The limiting reactant. All right, so up until now, every conversion we've done, every switch over from one molecule to another has been based on the premise that we just have the one amount of the one substance and then we use that to switch over to the other one. But in truth, when you do carry out a reaction, you typically have more than one reactant. And not only that, but you do have amounts given for each one of these reactants. For instance, in this combustion reaction between CH4 and oxygen, we could have 10 grams of CH4 and 30 grams of O2. And the question becomes, well, which one is going to run out first? Because now we don't have just one single amount, we have two amounts, and one of them is going to be present in the least amount. It is basically our task whenever a problem of this sort, when we have the amounts of two substances given, to find what the limiting reactant is going to be, the substance that will run out first. All right, and by and large, anytime that you see the amounts of two reactants present in your problem, you ought to think automatically that this is a limiting reactant problem, even if you're not told so explicitly. Now, as I was saying, the reactant is going to be consumed first fully is known as a limiting reactant. And importance in this concept is that the limiting reactant is by default what determines the extent of the reaction, because the moment one of the reactants is fully consumed and fully gone, the reaction ceases to take place. So knowing which reactant is the limiting reactant will tell us the extent of the reaction. How much product can we make? How much of the reactants are we actually going to react away, etc., etc. So we're going to use stoichiometry to first figure out which one of the two reactants is going to be the limiting reactant, and then we'll use that information to perform a few extra activities. Okay. All right. So there's different ways to do this. I'm going to show you one very specific way to do it. This is the way I prefer to do it, but if you prefer to approach it from a different angle, different perspective, that's fine with me as long as you get the same answer. But the way I do this is to look after some product. Now the product, they might actually tell you in the problem, we want to find out how many grams of CO2 you're going to be producing in this reaction. Or they might not tell you that. The problem itself may just say, what's the limiting reactant? It's all the same. Pick a product, doesn't matter which one, pick a product, and you're going to use that product as your reference point. Now, ultimately, what we're going to have to do is stoichiometry. We're going to have to switch over from one molecule, specifically one of the reactants, and we're going to switch over to the product that you are looking for, or the product that you've chosen to make your reference point. But the idea is that we first will need to switch from the mass of the molecule to the moles of the molecule. So in the case of CH4, we have 10 grams. So we have the 10 grams. We divide it by the molar mass of CH4, which is 16.13 grams per mole. Grams go on the bottom to cancel out the units. But we also do the same thing with the other reactant, O2. We have 30 grams of O2, and we divide that by the molar mass of O2, 31.98 grams for every 1 mole of O2. What's going to happen is that the grams of either reactant are going to cancel out. Now we have moles of CH4 or moles of O2. Now that we're in moles, what we're going to do is switch over from the moles of either reactant to the moles of the very same product. And the reason why is because we're going to use the amount of the product as our basis of comparison to determine what the limiting reactant actually is. Okay, so here we go. We're going after CO2 since we want to find out the mass of CO2 anyway in this problem. So we look at CH4. There's one CH4 for every one CO2. So this ratio is going to be 1 to 1. But looking at O2, there's two molecules of O2 for every one of CO2. And what that means is that even though the first set of conversions will be a 1 to 1 ratio, the second one will be a 1 to 2 ratio. And the 2 is on the bottom because on top we had moles of O2, so the moles of O2 still have to be on the denominator of this fraction. And since the O2 has the coefficient of 2, that's where number 2 goes. That sounded kind of funny. All right, now moles of CH4 and moles of O2 cancel out. We now have moles of CO2. Now, technically speaking, you could stop at this point to make the comparison. And if the problem is only asking for you to find the limiting reactant and there's no other mention of the amounts of the product or anything like that, you could pretty much stop right here. But if you do get asked for the amount of the product, like the grams of the product, then it'll be best for you to actually do that. Go from moles of the product to the mass of the product using the molar mass. So the molar mass of CO2 is 43.99 grams per mole. That will apply to both equations. And the moles of CO2 are going to cancel out. We will now end up with mass of CO2. So what we do is carry out the conversion. 10 divided by 16.13, you press enter. Then you multiply that by 43.99 and you press enter to get the first result. For the second conversion, you take 30 divided by 31.98, press enter, divided by 2, press enter, multiply by 43.99, press enter, and you should find out the following two numbers. All right, now this is the way it goes. Because the premise is such that one of the reactants is going to run out first, by default, this creates an upper limit to how much product you could possibly get. And what that in and of itself means is that whatever amount of CO2 you're getting, as far as comparing these two numbers, the number has to be the least amount. Because that will tell you this is as much as you can get if all of the O2 runs out. And once that runs out, you get 20.6 grams. There's no way you're going to get 27.3 grams if you have no more O2 present to begin with. So just by looking at these two numbers, automatically you go with the lowest one. That will tell you that the lowest amount is the one coming from O2. And you also get another benefit out of this thing. The moment you identify the limiting reactant as being O2, you also get something known as the theoretical yield. Specifically, the number that you get right here, the mass of CO2 product that we calculated using stoichiometry, is what we call the theoretical yield. And it comes directly from performing stoichiometric calculations like the one right here. So this process, I like it a lot because it's technically a twofer. It gives you the identity of the limiting reactant and the amount of yield that you expect to get in theory, provided that you don't miss any reactant, that you collect every single amount of product that you are making. And one more thing that I'll say before I end the video, when you're asked for the limiting reactant or to identify the limiting reactant, as the name implies, this has to be a reactant. It, don't ever say when asked this question that the limiting reactant is the 20.6 grams of CO2. First of all, CO2 is not a reactant, so that I won't take that answer as a correct one. The reactant, the limiting reactant, is indeed O2, because O2 is the reactant from which you started the entire conversion that led to the 20.6 grams of CO2.